This video is part of an online course on linear algebra and will be about systems of linear equations. In this video, we are going to first see how we can write down what a system of linear equations are in a formal way and hint towards how we are going to go about solving such a system of linear equations in a systematic way. So we want to model the case where we have m linear equations in n variables. The coefficients of each linear equation is going to come from an underlying field f. Recall that for this course, f will always be a subfield of the complex numbers. See the previous video for a precise definition of what a subfield of complex numbers means. So we have this underlying field f, which we will often call the base field. And we have m linear equations in n variables. So we can write down the linear equations in this way. The first equation we can write down as a11 x1 plus a12 x2 plus dot 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 a1n xn is equal to yn. In an analogous way, we can write down the rest of the equations a21 x1 plus a22 x2 plus dot 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 plus a2n xn equal to y2, and dot 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 you have m equations, so the final one would be a m1 x1 plus a m2 x2 plus dot 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 a mn xn equal to ym. So we have this system of m equations in n variable. We are just going to denote this system for our convenience by star so that we can keep referring back to this throughout the rest of this video. Now the goal, let's write that down because this is sort of like a central goal of the first part of the course. Goal, find, of course I must mention that here aij are elements of f where 1 less than or equal to I is less than or equal to m, 1 less than or equal to j is less than or equal to n, and y1 to ym are also coming from the field f. Okay, that was implicit in when I defined the system, but let's make it precise. Okay, the goal is to find x1 dot 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 xn coming from f such that the m equations are satisfied. A very modest goal, if I might say. Okay. Now there is a special case that is interesting and it's going to play an important role in the theoretical development of this also. So let's note that down. If y1 equal to y2 equal to dot 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 equal to ym is 0, then we say the system star is homogeneous. Okay, now how would you go about solving such a system? Well, the real best way to go about solving the system is to write down a pair of equations or some and try to see how to solve them. I'm going to start with a pair. I'm going to just write down random coefficients and random equations, and because I know a bit of linear algebra, I know that there is going to be a solution and I will not be in trouble. So that's why I'm going to write down random stuff. So I've written down two equations at random. X plus y minus 3z equal to 4 minus x plus 3y plus 2z equal to 6. Within a few hours more of videos in this course, you will understand why. But this system is definitely going to have a solution. Okay. How would you go about solving this? Well, you go about solving this in the way you would do it for two equations in two variables, which you would have no doubt solved hundreds of in your school. You just add both equations and you will get 4y plus z equal to 10. Adding both equations got rid of the variable x, thankfully. Now what we need to do is we need to understand how to solve 4y plus z equal to 10. But observe that if I set z to be anything, this is the key, anything in the field f, I can solve for y. Okay, so if denoting z, takes z to be some element a in the field f, then you know that y has to be 10 minus a divided by 4. Just a second, this a looks like 9, so make sure there is no confusion. Because of typography, I'm going to make it look like an a. So if you set z equal to a, where a could be any element whatsoever coming from the field f, you know that y equal to 10 minus a by 4 is going to be a solution. Okay. Now substituting back in the very first equation, you get x plus 10 minus a by 4 minus 3a is equal to 4. Okay. So which just means that x equal to 4 plus 3a minus 10 minus a by 4. And I am not even going to bother simplifying this to get a better expression for x. You now know that this system has solutions. In fact, it has plenty of solutions. Z can be anything whatsoever. The moment z is fixed to be a number a, there is a unique y that you get as a solution, and this x, z and y together determine a unique x. So in some sense, this system has a solution space which is one dimensional, 1 degree of freedom. You can choose whatever you want for z, but the moment you do that, you are forced to choose a particular y and a particular x. Okay. So how did we solve this system of equations? Well, we did some algebraic combination of the two equations, eliminated one of the variables that forced once you eliminated one of the variables, you ended up with one equation with two variables. So if you set one of the variables to whatever thing you like, the other variables are sort of fixed. Okay. Now I want you to ponder over one interesting observation. At this stage, you could have, instead of taking z to be a and solving for y in terms of that fixed a, you could have done the opposite. You could have fixed y to be a and solved for z. Okay. Now, do you get exactly the same set of solution if you had made that choice? Well, please ponder over that. Okay. So essentially what I want you to ponder over is whether we have gotten every single solution to the system that we have considered by this procedure. Now let's formalize what is going on. Okay. So we had this system star. Let me flash that back to you again. Now obviously if I multiply one of the equations by some constant c, where this constant is coming from the field f, then if this equation is satisfied, then so is this equation, right, for obvious reasons. In a similar way, if I multiply the first equation by some constant c1 and the second equation by some constant c2, when I say multiply the equation, I mean both sides of the equation, both here as well as here, on each one of the coefficients as well as the right hand side. Now observe that if I multiply throughout by c1 and c2 and add, then if you had a particular solution for the first equation and a particular solution for the second equation, then when you multiply and add, the equations will still be satisfied. Okay. So what I want to say is, if if x1 to xm in F satisfy star, then for any c1 dot dot c2 dot 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 cm coming from the field F, so this should be x1 to xn because there are n variables. If x1 to xn coming from the field satisfies the system star, then for any choice c1 to cm in F, the equation c1 into a11 x1 plus dot 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 a1n xn plus c2 into a21 x1 plus dot 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 a2n xn plus dot 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 cm into am1 x1 plus dot 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 amn xn equal to c1 y1 plus dot 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 c2 y2 or not dot 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 plus c2 y2 plus dot 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 plus cm ym is also satisfied. Okay, now this combination of equations is called a linear combination. This is called a linear combination. So if you have a bunch of equations and you take a linear combination, that is multiply each equation by some scalar and add them up together, then if you have a solution for the original system of equations, then that same will satisfy this linear combination. Okay, so let me just state a theorem whose proof should now be self-evident to you, so much so that I am not going to give the proof. I want you to ponder over it. It's that trivial theorem. Oh, before that, let me make a definition. Definition: two systems of m equations in n variables are, actually you don't need to say two systems of equations in n variables are said to be equivalent if each equation of the first system is a linear combination of the equations in the second system and vice versa, which means each equation in the second system is a linear combination of the equations in the first system. So two systems of linear equations are said to be equivalent if each equation that is occurring in the second system I can write down as some combination of the equations in the first system, and I can do the same for each equation in the first system in terms of the second system. So all this is much ado about nothing, because the next theorem is rather trivial, and I recommend that you don't spend more than 5 minutes trying to prove this theorem because it's that easy. Equivalent systems of linear equations have exactly the same solution sets. Okay, so please spend a few minutes trying to prove this theorem, no more than that. With this theorem at hand, there is a light that we can see, a path that we can take. Start with a system of linear equations, make it into a simpler system, simpler equivalent system by applying this elimination process, solve the simpler system. In the next video, we are going to see a systematic procedure for doing this, which is now known as Gaussian elimination. But as you can understand from the introductory video, this method was known for a rather long time, much before Gauss. So this Gaussian elimination system allows us to solve a system of linear equations by systematically reducing it into a simpler system. And for the purposes of applying Gaussian elimination, it will become very clear that what is actually relevant are these coefficients a11, a12, a1n, and these variables that you write here are just an unnecessary distraction. For the entire purpose of applying Gaussian elimination, you need to focus only on these coefficients. So what we will do is we will take all these coefficients, bunch them all together in a box and call that box a matrix. So we will essentially apply Gaussian elimination on matrices. Not only is Gaussian elimination a method of solving a system of linear equations, we will get a lot of information about the solution set by Gaussian elimination. Stay tuned for the next video. This is a course on linear algebra and you have just watched the video on systems of linear equations.